Hello, my name is Kokorin. I'm a senior database developer at vk.com, and I present you the talk Model-Based Testing of Practical Distributed Systems in Actor Model. So our journey begins with our engineering team developing a strongly consistent, replicated databases for vk.com. In order to achieve that, we implemented a consensus replicator called Barsik. Barsik is a common name for a cat in Russia. This is why its logo resembles a three-way replicated cat. Barsik architecture is quite ordinary and resembles, for example, TIDB architecture. The database is sharded. Each shard is replicated and has a single elected leader. Upon leader's death, another replica is promoted to leader. Write queries must be processed by the corresponding shard leader, while read queries may be processed by any replica. Barsik supports a couple other features, such as witnesses and observers, but I won't go into technical details now. Barsik implementation is based on view-stamped replication algorithms, one of the many existing strongly consistent replication algorithms, similar to Raft, Zookeeper, Atomic Broadcast. The view-stamped replication algorithm is well known, heavily tested, its correctness is proven. Therefore, merely implementing it led us to production-ready, strongly consistent replication engine. Can you believe this? Yeah, me neither. Things never go so smooth in production. Indeed, merely implementing an algorithm from a scientific paper is quite a simple task for a skilled engineer. Often, distributed algorithms even fit in a single page. But algorithms from scientific papers often turn to be impractical, and therefore it's impossible to use such algorithms in production systems as this. For example, the view-stamped replication algorithm requires periodically sending the whole database append-only log to peers, which is absolutely impossible in real-world scenarios when the database log can be in the order of terabytes. Therefore, we have to optimize the protocol to send only the modified suffix of the append-only log. Furthermore, algorithms from scientific papers often lack features required in production. For example, Barsik must support splitting overloaded shard into a distinct subshards, storing distinct subsets of the data stored on the initial shard. However, the view-stamped replication algorithm does not describe such a splitting procedure. The original paper does not say anything about sharding at all. We may also want to add other new features to the algorithm, such as implementing the number of replicas, limiting the number of replicas running garbage collection concurrently. We need this feature because if too many replicas of the shard start the garbage collection procedure concurrently, it will severely hinder shard's ability to respond to queries in time. Of course, both above-mentioned problems are solvable. A skilled engineer can tailor an algorithm for the production needs. However, the resulting algorithms will differ significantly from an algorithm from the paper. Therefore, it will not be heavily tested and proven anymore. It's not just our problem, it's ubiquitous for the whole database development community. A lot of engineering teams state that they had to heavily modify the algorithms their systems are based on to tailor them for the production needs. Personally, I like the quote from the Google engineers, stating that almost every production system is based on an unproven protocol. It means that we have to heavily test our system without relying on the correctness of the underlying protocol, because the implementation of the protocol can be incorrect in two senses. First, incorrectly implemented optimizations can break the initial algorithm invariance. Secondly, new features can be implemented incorrectly and work poorly in some cases. The most widely used testing approach consists of running the system under test as a system of distinct processes working in parallel, while introducing random errors, such as dropping messages via IP tables and killing processes with the kill utility. We want our testing method to be reproducible. Once we find an error's execution, we can repeat the very same execution as many times as we like for debugging purposes. However, this approach is not reproducible at all, because we cannot force parallel processes to repeat the actions in the exactly same order. One possible solution to this problem is to implement the system in the Hewitt's actor model. The system is said to be implemented in the actor model if it is implemented as a collection of actors. Each actor contains private state, inaccessible to other actors, works sequentially, and can react to incoming messages. During the processing of a message, actor modifies its state and may send a number of events to other actors. We may simulate the execution of an actor system step by step. On each step, we take a single unprocessed message and delivers it to the corresponding actor, and that actor modifies its state during the processing of the message. The actor may also request to send a couple of new messages, which are added to the set of unprocessed events, and will be sent to other actors in their turn. The processed message is then removed from the unprocessed set. Of course, in production, actor systems are never executed step by step. Instead, production actor frameworks such as Akka or C++ actor framework runs actor in parallel on multiple nodes. But during the test, we can use step-by-step execution to allow deterministic replay of errorless execution. On some steps, we may introduce deterministic errors. For example, we may corrupt a message or delete and forget an unprocessed message to simulate an unreliable network. To simulate network partition, we may stop delivering messages to a particular actor. To simulate crash and recovery of an actor, we may delete that actor and recreate it later with a blank state. In this model, each execution is a sequence of events and errors, which can be deterministically replayed as many times as possible. In vk.com, we use fuzzing as well to generate interesting execution scenarios. But in this work, we focus on using TLA Plus and TLC to check all possible execution scenarios within the given constraints. We use TLA Plus to implement a model of the system. Model state consists of an array of actor states and initially empty set of unprocessed messages. On the slide, we can see the initial state of the Barsic replication algorithm model. We then describe each possible transition of the system. Each transition corresponds either to processing of an event or introducing of an error, such as message corrupt. During message processing, a single actor modifies its state and may add new messages to the unprocessed set. Finally, we specify the invariants that must hold during each possible execution. For the replication algorithm, we state that the committed log prefixes must not differ between any pair of replicas and that the whole log must be committed eventually. We use neither +call nor any other tool that turns imperative code into a TLA specification. In vk.com, we use specification first approach. We first write the TLA plus specification, check it using the TLC model checker, verify that the algorithm is correct, and then write the code based on the specification. If we want to modify the system, for example, when we want to optimize the append-only log synchronization protocol, we first modify the specification, check the new specification, and then modify the imperative code based on the new specification. After the system stage, all transition and all the invariants are specified, we run the TLC model checker. TLC model checker builds the system transition graph and checks that all the invariants hold in each possible execution within the given constraints. We must constrain the system to make sure the system transition graph stays finite. Limiting the maximal number of process events works in all cases. However, we may exploit other constraints as well. For example, for the replication algorithm, we may limit the number of leader elections and the number of requests processed per leader. The big question is whether the code behavior is consistent with the model or we have made some bugs during the implementation. We want to generate a set of tests to check our implementation. Let us see what the set of tests looks like. Each test is a path in the transition graph, starting in the source node. This path corresponds to a sequence of events processed by actors of our system. This set of tests must be exhaustive. It must cover each edge of the transition graph at least once. Note that covering each node is not sufficient, since we must check that processing of each event in the implementation is consistent with the processing of that event in the model. For example, In the example from the slide, a single test E1, E3, E4, E5, E6 is not sufficient even though it covers all nodes. It must cover all edges. At least 2 tests are required to cover each edge of the graph from the slide. We want to make this test suite as small as possible to run our tests as fast as possible. Let us now see other solutions to this problem. The first solution is modulator. It uses Apalache model checker to generate tests for a Python program with a specification written in TLA+. It has 3 major drawbacks. It supports neither Go nor C++, which we use for database implementation. It generates only random tests without building the whole transition graph, and it supports only a small subset of the TLA+ language. The second solution is Kaifabe, which was discussed at the very same conference 5 years ago. Kaifabe supports only C# and reduces test generation problem to a traveling salesman problem. This has 2 important consequences. First, it guarantees visiting each node at least once, without the guarantee to cover each edge. Second, since the traveling salesman problem is NP hard, Kaifabe has to either use exponential algorithms or use approximate algorithms. Kaifabe after states that they support systems with only hundreds of states, while our tool supports systems with tens of millions of states, which I will show in the performance section. The tool by Wang et al. Is just much slower than our tool. It executes one test in a couple of seconds, up to 10 seconds, while our tool is capable of executing thousands of tests per second per core. We reduce the test generation problem to a minimal circulation problem. Suppose we are given a multigraph, and for each edge we are given lower and upper flow bounds, and the cost of the flow unit over that edge. For each edge, we must find the flow value between the lower and upper bounds such that the flow incoming to each node equals the flow outgoing from that node. From all suitable flows, we must find a flow of the minimal total cost. The problem can be solved in polynomial time using Goldberg and Taryan algorithm. To find the minimal exhaustive test suite, we add a reverse edge from each node to the source node of the transition graph generated by the TLC model checker. After that, for each added reverse edge, we set flow lower bound to 0, while for each edge of the original graph, we set flow lower bound to 1. This way we require non-negative flow over each edge of the original graph. Upper flow bound is set to infinity for each edge. After that, we solve the circulation problem in polynomial time using Goldberg and Taryan algorithm. After that, we create a flow graph by repeating each edge the number of times equal to the flow value over that edge. Since we have non-negative flow over each edge of the original graph, each edge of the original graph exists in the flow graph at least once and may be repeated multiple times. Some added reverse edges may not exist in the flow graph, since the flow over them may equal 0. The flow graph has an Eulerian cycle, which can be easily proven from the circulation definition. The Eulerian cycle can be found in polynomial time and covers each edge of the flow graph. Since each edge of the original graph exists in the flow graph at least once, the Eulerian cycle covers each edge of the original graph at least once. To find the exhaustive test suite, we traverse the Eulerian cycle. Each time we follow a reverse edge to the source node, we start a new test. Therefore, from the example from the slide, the exhaustive test suite consists of 4 tests. Such a test suite covers all edges of the original graph at least once, and therefore this test suite is exhaustive. After that, each pass can be transformed into a sequence of events, starting in the initial stage and executed as a test. To minimize the total per test events count, we simply set the cost of a flow unit to 1 for edges of the original graph and to 0 for reverse edges. This way, finding the circulation of the minimal cost minimizes the total flow over the edges of the original graph, thus minimizing the number of traverses over the edges of the original graph, which leads to minimizing the number of processed events. We have algorithms for minimizing the number of tests and maximal test length as well. To execute the test, each actor of the implementation must implement toModel method, which transforms state of the actor into a set of TLA plus variables. For view stamped replication algorithm from the slide, it should return status, view number, commit number, download replica, catch-up pos, and phase 2 variables. During execution of a single test, after processing each event, we check that state of each actor of the implementation is consistent with the state of the corresponding actor of the model. We do it by comparing two states of TLA plus variables, the one from the model and the one returned by toModel method. Our tool supports some graph pruning techniques as well that let us reduce the size of the graph. For example, consider two messages, M1 and M2, destined for two different actors and existing at the process set at the same step. Processing M1 and then M2 always leads to the very same system state as processing M2 and then M1. Thus, one edge of these four can be removed from the graph and not covered by tests. Here we can see the experimental results of applying our tool for verification of the Barsic reconfiguration subsystem with different parameters and constraints. In all cases, generating a test suite takes less time than building and checking the graph using the TLC model checker. It can be seen that our tool is capable of processing systems with tens of millions of states and hundreds of millions of transitions. The same applies to test execution. Since different tests can run in parallel in different threads, test execution algorithm scales linearly and handles big graphs as well. To test the system, our tool builds and checks the model transition graph using the TLC model checker, finds an exhaustive test suite of the minimal size on this graph and executes these tests. The longest practical testing time took 93 minutes to generate the graph, 69 minutes to calculate the test suite, and 24 minutes to execute 64 million test cases on a single core. Therefore, on a relatively big graph with 14 millions of nodes and 129 millions of edges, our system generated and executed almost 6,000 test cases per second, which makes our solution much faster than our counterparts. We continue on active research and engineering work in multiple directions. For example, we are experimenting with advanced graph pruning techniques. We're generating random execution paths instead of building the whole graph, and more sophisticated minimization algorithms. Thank you for your attention.